Recall, in physics, all measured quantities are either, I'm looking for a word that begins with an S, I'm looking for a word that begins with a V. Scalars or vectors. And that's going to become much more important this year than it was last year. Scalars have something only. Sarah, magnitude only. Size. Put your pencils down, look up. Patrick, what two things do vectors possess?
Direction and magnitude.
They have both magnitude and direction. It's always nice when Hollywood gets the math right. So here's little Patrick the puppy. Patrick the puppy is going to go wandering around his neighborhood. It looks like he makes a bunch of short little trips. He travels 3 meters and stops, 2 meters and stops, 4 meters, 4 meters, 2 meters, 4 meters. In fact, we've represented the trips with a series of arrows drawn on the physics teacher's front lawn. And each arrow has both a magnitude, size, and a direction of these successive trips. These are displacements. We call these vectors. When Patrick reaches his final spot, right there, how far has he traveled? Well, it really, Ira, depends on what you mean by how far. If you're interested in the number of steps he took, the distance, symbol D or X or S, various symbols for distance. I'll use D for distance. Well, he went 3 plus 2 plus 4 plus 4 plus 2 plus 4. 3 plus 2 plus 4 plus 4 plus 2 plus 4. Was that right, Mr. Dewick? Yeah. How far did Patrick travel? 19 meters. What if you want the displacement? Displacement only asks what's his change in position. We don't care how he got there. We just care, Josh, where did he end up? In fact, really what we're talking about is that little line right there from the diagram, that slanty line. Wait. I can fill in a little bit more. I think by looking at the diagram, I can imagine that that line is part of a triangle. How long is the base of that triangle if you look from the diagram and kind of move numbers around in your head? How long does the base of that triangle have to be? I think 4, yes? And what about the height of that triangle? I think 3? Oh. I can now figure out exactly how long the black line is. Looking for a word that begins with the letter P and rhymes with Pythagoras. Pythagoras. I think if you go 4 squared plus 3 squared equals and square root, this works out to a nice even answer. 5, yes? Yeah? Oh, this would be a displacement. We would symbolize that with a D and a vector symbol. Sorry for those of you on YouTube, I just sneezed into the microphone. Take your headphones off next time. Meters. But then we need a direction. To show that we're doing a direction, we do an @ symbol, like the symbol that appears in your email address or in your Twitter handle. As a lefty, I have a real problem, Ange, drawing the @ symbol. It's going to get messier and messier. For me, the @ symbol that way is nice, but that's not how the @ symbol is written. It's written for righties, so it's just going to get messier and messier and messier. To give the direction, the first thing I would like to do is give you the angle. Well, I think in the diagram, they gave you that angle there, did they not? How big is that angle? 53 degrees. However, that's not inside my little triangle. I would like this angle right here. How can I figure out how big that angle is? Taro? Okay, so they add to 90. Angles that add to 90 are called complementary angles. My mommy says when I'm being nice, I'm being complimentary. Zach, she means something different. Complementary angles in math add to 90 degrees. And so how big is this one down here? 30 what? 37 degrees. So we would write the direction as 37 degrees north of east. What? I'll teach you that last part in a bit. But if you gave that vector to a physics person, they could be able to reproduce that black line bang on, magnitude and direction. There are two ways to write a vector quantity. In textbooks, they use bold font, but when you're handwriting, to try and somehow bold font everything, hey there's a bold font for a letter P for momentum. It's irritating. So instead what we do, momentum is the vector. We draw an arrow above the letter. We used to draw a full arrow, but over the centuries, it's just become kind of a half arrow. That's the symbol for vector. That's to indicate it can be represented with an arrow and it has direction. If a textbook wants magnitude only, in other words, if it wants to show the difference between speed and velocity, it uses plain italics. Again, that's tough to handwrite, Zach. So if I want magnitude only, I will often use the absolute value symbols. The same way in math, you learn that that just gives you the magnitude, the positive answer, the size, doesn't care about negative or positive, same idea. Or I will write the words, give me the magnitude only. More likely on a test page, that's what I'll end up doing. Mr. Dewick, this 37 degrees north of east is kind of weird. We'll come back to that. If you add 5 kilograms of sugar to 3 kilograms of sugar, Jaden, what's 3 plus 2? Did I say 5 kilograms? 3 kilograms of sugar to 2 kilograms of sugar. What's 3 plus 2? What's 3 liters of water and 2 liters of water? What's 3 plus 2? In scalar mathematics, as long as the units match, you just add the numbers like standard arithmetic. Now, that doesn't work for 3 kilometers plus 1 meter, or 3 kilometers plus 2 seconds. Obviously, the units have to match. But masses and volumes, they add together with the rules of normal arithmetic. We call them scalar quantities. They have magnitude but no direction, much like some of your career ambitions. Other scalar, I just made that one up. That was pretty, no, nothing? First time I used that one. Other scalar quantities are, can you give me something that you remember was a scalar from last year? Speed. What else was a scalar? Distance. Give me a second here, we'll pause the video. Another scalar that's going to become very important this year is work and energy. We're going to use work and energy to analyze roller coasters. And the reason we're going to use work and energy to analyze roller coasters is roller coasters are yucky, curvy paths. To try and analyze that vectorially, even with calculus, would be a chore. In fact, you're going to hear me say one of the trigger points we're going to learn later this year. Is there a yucky, curvy path? That's a job for energy. Voltage, you'll learn later, is a scalar. Has magnitude only, but no direction. Now, these can be negative or positive, because a negative is still a magnitude. It just means a loss of something. If you add a 3-meter displacement to a 2-meter displacement, Jaden, those could add to 5. If you go 3 meters east plus 2 meters east, that's 5 meters east. However, if you go 3 meters east plus 2 meters west, that's 1 meter east. And you can get every single decimal value in between if you add east plus north. This is added together using the rules of vector mathematics, and I'll explain how that works in just a second. But you can see perhaps why I did a review of trig. We're going to be doing triangles quite a bit. What are some other vectors? So displacement. What are some other vector quantities? Velocity. What else? Do you remember? Yep.
Displacement.
Displacement. What else? Momentum was. That's going to come back to bite us big time this year. When we look at momentum collisions at angles, you're going to find they are the second longest question of the year in terms of amount of work. They'll take about 3/4 of a page per collision. There is one question that's going to be longer. When we put things into orbit and we calculate how much work it takes to put something into orbit, ironically, the amount of work it takes to calculate how much work, it's a lot of work. That'll be about a whole page to get one answer. But then there's the glory feeling at the end of, ha ha, I got it. What else?
Force.
Yeah, force. Absolutely matters which way you push on something. Taylor, if I add 7 newtons and 4 newtons, what's the maximum answer I can get? Yep, what's the smallest answer I can get? Right, because you could, in other words, 7 plus 4, same direction, 11. 7 plus 4, opposite directions, 3. 7 plus 4 at a slanty angle, every decimal in between. Before we do 3 newtons, Mr. Dewick. Before we do vector mathematics, I need to teach you how we write directions. So this is the convention for giving directions. It's a little bit tricky because the way you say it in English is sort of backwards from the way that you think it should be. All of you have just turned the page, yes? We're going to be writing compass directions, so I'm going to insist all of you somewhere on the page right now. Anytime I'm dealing with a compass, I almost always stick a compass rose somewhere on the page because that avoids mistakes. And this first angle we're going to look at here is this 28 degrees. This 28 degrees. Tato, do you notice that 28 is made up of 2 lines, a slanty line and a nice line? Do you understand what I mean by a nice line, a non-slanty line? Okay? To show that we're giving a direction, we typically write an at symbol as our introduction. We write the angle 28 degrees. Then I'd like you to leave a space for a letter and write the word of and leave another space for a letter. Tato, see the 2 lines? See the slanty line? See the nice line? What direction is the nice line pointing? The nice line always goes after the of. Always. Tato, if I start on the east, what direction do I have to go to touch the slanty? We would say this is 28 degrees north of east. Start out going east and then go 28 degrees north of east. Next one. At 51 degrees. Gurjot, see the 2 lines, one slanty, one nice. What direction is the nice line pointing? So it's going to be of north. From this nice line, what direction do you have to go to hit the slanty? This would be 51 degrees east of north. That's how you would write that angle. That's how you would give the instructions to anybody else so they could recreate that angle. This next one, it's going to be at 20 degrees. What of what? North of south, east of west? What of what? Linnea, see the 2 lines? One slanty and one nice. What direction is the nice line? So it's going to be something of north. Which way do you have to go of north? See it? I start out going north. I have to go that way, which is, yes, 20 degrees west of north. This is tricky. One of the smartest students I've ever taught, Dylan Gattner, Tato, you probably played some hoops against him. He could not figure this out. He came in one day after school, and I wrote out all 16 different combinations, and he just memorized them all. Okay, so that's what west of north looks like. That's what north of west looks like. That's what south of east looks like. That's what east of south. Okay, done, Mr. Dewick. I hate memorizing, so I'm going to suggest it's better to learn how to write these. This is going to be at 48 degrees. North of south, east of west, what of what? South of west. The nice line always goes after the of. Start out going, and by the way, when you think of it, hopefully it makes sense now. You start out going west, and you go south of west to draw out that angle. Try this one on your own. I'll do it up here. Yes? West of south. Start out going south. Go 78 degrees west of south. Sound effects are optional, but sometimes they help. (52 degrees north of south, east of west, what of what? South of east. Now, if this was all there was, that would already be bad enough, but it turns out each of these can be written two ways. Let's go back to the very first one. How big is that angle? I'll give you a hint. They're complementary. Oh, that's so nice. They're so nice complementary. How big is it? You could also say 62 degrees. Now this time that vertical line would be the nice line. So of north, what direction? 62 degrees east of north is the same as 28 degrees north of east. I will take both answers. Often in my answer key, you'll see I've written both answers, and you don't have to give me both answers, but it's just so that when you're checking to see if you did it right, it all depends on which lines you chose to draw first in your vector diagram, and we'll talk about that. This one here, how big is that angle? So also 39 degrees north of east. And by the way, the pattern for complementary angles is the direction letters just switch places. So instead of east of north, north of east. Just for giggles, let's do the very, very last one. This 52 degrees, it's also 38 degrees east of south. So often in my answer keys, you'll see I've jotted down both answers. Sometimes I forget to, so if you get the complement, you'll know you're right. Vector addition in one dimension. Vector addition in one dimension. Sharon, my angel, what's 5 east plus 3 east? Yeah, 8 meters. We'll put an at symbol, east. By the way, even if there's no angle, I'll often put an at symbol, especially if we're dealing with north. Don't write this down. But an N right there, that's north. An N right there, that's newtons. An N right there is a subscript, that's normal force. Like, have I gone on my rant about how we need more letters? So my workarounds will try and be as clear as possible. And if I'm going to do a direction, I'll often put an at symbol to say everything after this is not a unit, it's a direction. Also, capital S looks like a lowercase s, seconds. And also, W is watts for power, and west. Okay. Hey, Paige, what would 6.2 left plus 6.7 right be? And then the units would be newtons, and then I would write out the word right, or you could say at right. Right's not really a compass direction, so I usually write it out. Those two answers, the 8 and the 0.5, that third vector represents the sum of the first two vectors. We have a fancy name for that. We call it the resultant. When you add two vectors together, the combined answer is called the resultant. Heck, when you add more than one vector together, the answer is the resultant. Physics 12 starts now. Adding vectors in 2 dimensions. This is the brand new stuff. I've already told you that we represent vectors with arrows, and one way to add vectors together would be to get a ruler, get some graph paper, get a protractor, and Josh, we could draw everything to perfect scale, measuring very, very carefully, doing meticulous blueprint style diagrams, and then at the end, wherever you ended up, you could then measure that distance, go look at your scale, multiply by the conversion factor, use your protractor to get, or better yet, you can use some trig. Way easier. Here is the key to today's lesson. To add two vectors together, we draw them tip to tail. Josh, how do I draw them? Mobeen, how do I draw them? Alec, how do I draw them? Zach, I want to add two vectors together. Any suggestions on how I might want to draw them? Tip to tail, you say. Taylor, let's suppose you wanted to advise somebody on how they could add two vectors together. How would you recommend that they draw them? Tip to tail, tip to tail, tip to tail. Chang, knock, knock. I want to add some vectors together. Any thoughts? Tip to tail. Okay? That is the key idea. And then once you've drawn, now I realize right now you don't know what tip to tail means, but this is going to be the acronym dumb thing you're going to remember. And then the resultant is the line from the tail of the first vector to the tip of the second vector. I was going to show you a Java app, but it's kind of lame. Instead, we're going to do example 4. Turn the page. Normally, you'll have this in front of you, but since we've turned the page, we're going to quickly redraw it. Example 4 said 5 kilometers west and 8 kilometers north. So here, I'm going to write 5 kilometers at west, and I want to add 8 kilometers at north. Are there compass directions in this statement? Did you just turn the page? You don't have to, but you'd be wise to. Stephen, you're new to my class. I think everybody else might remember this. What does DULP stand for? When in doubt, DULP. Draw a little picture. So Stephen, draw a little picture. I have 2 strategies. One is defic, which I'll explain later, but DULP. When in doubt, defic and DULP. Draw a little picture. So we're going to draw a little picture, and I'm going to try and draw them roughly to scale. And what I mean by that is 8 is almost twice as big as 5, but not quite. So my line for 8 is going to be almost twice as long as the line for 5, but not quite. 5 kilometers west. Draw a line like that and call it 5. Plus 8 kilometers north. That's a little longer than the 5. That looks about right-ish, kind of. Equals. I want to add these 2 vectors together. Ange, how should I draw them? Okay, we can't stutter on that. It's going to be important. What does that look like? Watch. What's the first vector that I drew? 5. There's the tip. The tail of the second vector starts there. There's the 8. That's what I mean by tip to tail. The resultant is from the tail of the first to the tip of the second. It's kind of obvious. Oh yeah, it's pointing up that way. I'll call this capital R for resultant, and you may notice we have just drawn what shape? More specifically, what type of a triangle? A blank-angled triangle. In other words, Pythagoras and trig. Okay? This is how you add directions together. You draw them tip to tail, and you find the resultant. Can you please do the Pythagoras on your calculator, showing no steps, please, and give it me to 3 sig figs? It's going to be 8 squared. It's going to be 65 and 25. Sorry, 64 and 25. It's going to be a square root of 89. 9 point something. I'm going to say 9.3 or 9.4-ish. 9.43?
Yeah.
That's rounded off properly.
Yeah.
Units,
You put 3.43.
because my brain is dumb. Units. Direction. Now, sometimes I'll only ask for the magnitude because I figure to get the magnitude, you got to draw the vector diagram anyways, but here we want the whole schmear. Now, where does the angle go with? You'll notice there are 2 unknown angles here. You okay, Ira? What's your question? Oh, some of you, the calculators, when you take the square root, it's going to give you your answer in simplest radical form, and then you might have to hit either the S to D button on the Casios or the change button on the Sharps, or this is where you're going to learn your calculators, and I'll help you with it. Ira, do you notice there's 2 angles? Angle theta, the one that we're interested in, is always where the vector is originating from. So it's going to go there. And now I can find angle theta. That's 8, opposite, adjacent, or hypotenuse. Opposite. That 5, which trig function? Oh, you know another good habit that you should get into this unit anytime you turn the page? It's probably worth at the top of the page writing, or at the top of your test, write that right away, or in your homework, write that right away. So now I can cut down on my thinking. Which trig function? Tan. What always goes next to the trig function? Which in this case is theta, because I don't know it, it's a variable, equals opposite over adjacent. I think you'll find this angle works out almost bang evenly, and then I stopped trying to do that because it was a pain to get anything to work out evenly. Is it like 57.99999 or something like? I'm going from memory. I didn't do that in my head. So 58 degrees? Yes?
Yeah.
58 degrees. What of what? North of south, east of west, what of what? So there's theta. There's the nice line. There's the slanty. North of south, east of west, what of what? East?
What?
Yes. Okay. Zach, you okay with that? Zach, I drew the 5 first, and then I drew the 8. Maybe for giggles, you might have drawn the 8 first, and then drawn the 5. You get the same resultant, but your angle would have been this one, the complement. This is why I said there's always 2 possible angles. Or you could also have gone with 32 degrees west of north, and you would have gotten that if instead of going vector 5 plus vector 8, you drew vector 8 plus vector 5. Same diff. I usually draw them in the same order they give them to me just so that our diagrams look the same, but not always. Sometimes it will become very obvious. It's much easier to draw it the other way around. Is that all right? Force 1 is 10 newtons due east. I've scrolled down. You probably still have it on your page, but I'm going to do this. Force 1 is 10 newtons due east. Force 2 is 6 newtons due south. Find the resultant by adding them together. Hint, Dolp. Okay. Josh, how big is force 1, magnitude and direction?
10 newtons due east.
So I'm going to draw 10 to the east. There. Josh, how big is force 2, magnitude?
6.
Stop. I think 6 is a little more than half of 10. I'll draw that line a little more, roughly than half as long, eyeballing it. I certainly wouldn't want to draw it longer, because that would totally screw up my diagram. Direction.
So,
I want to add these 2 vectors together. Oh, piece of advice, number whatever I'm on. Draw your vector triangles medium to large. Every year I have some kid who wants to draw their vector triangles like that, and they always get stuff wrong. Also because your scale is all wonky. You can't kind of intuitively see where the angles are supposed to go. So I'm going to go 10, 6. Can you see the resultant, Josh? I think it's going to be pointing down and right from the tail of the first vector to the tip of the second vector. Since we're finding a force, I'll use the letter F for force and a subscripted of R for resultant. What shape is this, Josh, my friend?
Triangle.
What kind of a triangle? Hey, it's a right-angled triangle. Pythagoras and SOHCAHTOA are in play. So the magnitude, Pythagoras, is going to be 10 squared plus 6 squared equals square root. It's going to be the square root of 136. So it's going to be 11 point something. I'm going to go 11 point, there's a guess. 6?
Yep, 6, 1.
Oh, 11.7. Units, Josh?
Newton.
And because it's after the number and not after an at symbol, that's newtons and not north. Sorry. At. Theta always goes where the vector is originating from. So is it going to go top left or bottom right? Top left, where it's coming from. Sorry, I can't hear you. No, it's nothing. It's always where the resultant is coming from. So not where the resultant, you look at the arrow on the resultant, not where it's pointing to, where it's coming from. Nothing to do with the 10 or the 6. It's looking at your resultant. Good question. That 6 then, opposite, adjacent, or hypotenuse.
Opposite.
What about that 10? Which trig function? Mr. Dewick, the previous question was tangent, and this question is tangent. Are they always going to be tangent? Mostly. They'll be tangent if you're finding a hypotenuse. When won't they be tangent? Oh, in the next lesson, I'll give you some where I give you the hypotenuse. But for now, tangent theta equals 6 over 10. How big is angle theta?
31.
Sorry?
31.
31 degrees, is that right? Yep. Round it off properly. 31?
30.9.
Yeah, but 31 you said? Okay. 31 degrees north of south, east of west. What of what? I heard it. South of east. Now, I went 10 and then I went 6 down. If you started out going 6 down and then you went 10 over, you would get 59 degrees east of south. You'd get the same magnitude because the Pythagoras numbers would be the same if you go 10 squared plus 6 squared, or if you go 6 squared plus 10 squared. You're going to get the same thing there. The fancy word vector addition is commutative. Order doesn't matter. Let's do an application. Example 6. Until about 1998, and around 1997, 1998, President Bill Clinton declassified GPS. So until then, the limit that civilians could access GPS was, I think, within about 100 meters of accuracy. And then President Clinton asked the military to allow civilians to get the full GPS signal, which gets you to within a few meters. Anyways, until then, this is how pilots flew. Now it's done by technology, but I'm willing to bet, Jaden, pilots probably still got to know how to do it by hand as a backup, just in case something goes wrong. A plane, I've turned the page and I see the word north, so I'm going to draw a compass rose. Plane is flying due north at 132 meters per second. There's a crosswind blowing due east at 44 meters per second. What's their resultant ground velocity? In pilot speak, we call this your airspeed, the wind speed, and the ground speed. That bugs me. They should say your air velocity, your wind velocity, and your ground velocity, but they don't. It is a vector, though. And here's what we're really saying, and I even included this equation on your formula sheet in the first unit. What we're really saying is this. The velocity that the engines are pointing the plane at in this case, due north at 132 meters per second, combined with the velocity that the wind is pushing you at, that's what gives you your resulting velocity over the ground. In other words, I think I want to add two vectors together. Alec, any thoughts on how I'm going to draw them? Haley, what?
Oh, tip to tail.
Tip to tail, Captain Obvious. Thank you, Haley.
Sorry.
Alec, my friend,
Yes.
can you read to me the first vector, magnitude, and direction?
132 meters per second north.
North. So I'm going to draw a line like that. I'll label it 132 plus. Alec, what's the magnitude of the next vector? 44. It's roughly 1/3 of 132, roughly. So I'll draw it about roughly a third as long. Direction? East. So I'm going to draw a line pointing that way, about a third as long. 44. I'd like to add these two together, Alec. How might you suggest that I draw them? How might you suggest that I draw them, Alec? You're killing me here.
I don't know what you want.
Tip to tail is what I want. We're drawing them tip to tail. Then we can do Pythagoras. We can't do Pythagoras until we have the triangle. How do I add two vectors together? Draw them.
Tip to tail.
How do I add two vectors together? Draw them. I'm coming back to you later on this week, my friend. It's going to look like this. 132. Thank you, by the way. You're making it more memorable, which helps everyone else. And then tip to tail. So there's the tip of the first, the tail of the second. So the 44 goes there. You could also draw 44 over and then 132 up, but I'll go in the order they gave them to me. And can you see, folks, the result? It looks like it's pointing up and right. And I'll call this one the ground because that's what they called it in the question. You could also label it with an R for resultant. I'd figure it out. This is a triangle. Now what can I use, Alex, to solve the triangle? Pythagoras and SOHCAHTOA. So let's do the Pythagoras. The ground velocity is going to be 132 squared plus 44 squared, square root of that. I get 139 to 3 sig figs, yes? And that's meters per second at. Again, Linnea, theta goes where the vector is originating from. Is it going to go bottom left or top right? Where is theta going to go? Bottom, because that's where it's coming from. So theta goes there. You got to get theta in the right place, because otherwise your opposite and adjacent will be incorrect. That 132, opposite, adjacent, or hypotenuse? The 132, that's adjacent. And the 44? Opposite. Which trig function? Which will often be tan. What goes next to the trig function? The angle. Opposite over adjacent. Also, because I've drawn this roughly to scale, look at angle theta. It's going to be less than 45. In fact, I have a feeling it might even be less than 30 or around 30. Like, it looks smallish. If I get 68 degrees, I've either got my triangle labeled wrong or my diagram is wrong. This is why it's worth drawing it roughly to scale. What do you get? Sorry? 18.4? Is that right?
Yeah.
Rounded off properly? 18.4 degrees. North of south, east of west, what of what? Yes. Or 90 minus 18.4, 71.6 degrees north of east. That's what you would get if you drew the 44 first, and then you went the 132 up. That'd be this angle down here, which isn't in my diagram. Mr. Duck, what if there's 3 vectors? You turn it into 2 vectors. What if there's 9 vectors? You turn it into 2 vectors. Show you what I mean. It says 3 forces are acting on the same object. 5.5 south, 8.6 west, 10.6 south. I'm going to say to you, there's probably 2 vectors in there that I can already combine into 1. The 2 souths. What if one of them was north instead of south? I would just go winner minus loser. But what if I had 7 or 8 north-souths? I'd combine all of those into 1 by going winner minus loser plus winner minus loser plus winner minus loser. What if I had several east-wests? I'd combine those into 1 by going winner minus loser. No matter what, you can turn it into 1 north-south vector and 1 east-west vector, and no need to memorize something new. So, 5.5 south, 10.6 south. Chang, what's that really? 5.5 south, I know you were zoning out. 10.6 south is equal to what south? You see how I talked loudly when you made your mistake so that no one noticed? Wasn't that clever? 16.1? Oh, I got to draw one of these because I've just scrolled down. 16.1, you said? What about my east-wests? What do I have grand total if I combine all those? I think just 1. 8.6, which direction? 8 is roughly half of 16, so 8.6 I'll draw a little bit bigger than half as long as the 16.1. Are you ready, sir? Alec, my friend. Yeah. I'd like to add these together. Any suggestions on how I might want to draw them? Yeah! So it's going to look like this. Now, I got to visualize this. You'll notice I'm going to go down first and then sideways to the left. So I'm going to draw the 16.1 over here so I have room to go sideways without running off the page. You kind of start to get a feel for how to draw these so you don't have to erase stuff or so that you're not accidentally going back over your writing or something like that. You kind of imagine what it's going to look like. And then the resultant always from the tail of the first to the tip of the second, down and left. This is going to be force resultant. Solve this on your own. I'll do this up here, and let's see if we end up at the same place. This is a job for Pythagoras. Geez, Duick. Is that right? I got 18.3 newtons. All right, by the way, you're seeing why I suggested if you can get good at Pythagoras and SOHCAHTOA, it's a good asset. Okay. One last time, Alec, my friend. Ready? How do I add 2 vectors together? Draw them. How do I subtract 2 vectors? That's tomorrow's question. Next lesson's question. There is a procedure for subtracting vectors, but instead we're going to get clever. We're going to turn them into addition questions, and then we can add them tip to tail, rather than learn a whole new procedure. Turn the page. I've told you before I like the Foxtrot comic series because Bill Ammond has a degree in physics. So this first one, Jason, the young nerdy child, is playing football with his older brother Peter. Peter says, Jason, what pattern did I tell you to run? Jason says, you said to go 10 yards out, then 10 yards to the right. What pattern did you run? I went 10 root 2, yards at a 45-degree angle. And are they the same thing? Well, if you had the vectors, sure. This is football, not math class. That's why you think I rounded to 2 decimal places. That's the first one. The second one, now Jason is the quarterback, and he's talking to his brother Peter, and he says, okay, here's the play. Go 40 yards downfield, then turn left and go 20 yards, then turn right and go 25 yards, then turn right again and go 30 yards, then turn right and go 30 yards, then turn left and go 10 yards, and then turn left and go 15 yards, then turn left and go 20 yards, then turn left and go 50 yards, and hit with the ball. Peter thinks for a while. Won't I be right back where I started? I can't throw very far, says Jason. Peter says, okay, here's a new play. I never get to be quarterback. For those of you who are wondering, and I know at least one of you is, we have taken this out to the field. We have run this football play, and the vector sum is 0. You do end up back where you started from. The physics here is correct. What's your homework? I have a sheet for you to practice drawing pictures. Look at the handout that I just gave you. Folks, back here, please. I'll give you about another 30 seconds. For what it's worth, this handout was given to me back in 1988, by my first-year physics prof. This is the same handout, except finally this summer, about 2 weeks ago, I retyped it because it had become so ratty from being photocopied over and over and over. So you're doing first-year university physics technically here too. All I want you to do is draw the pictures and label them. So vector A plus B, I would be looking for that. I would be looking for that tip to tail, and then I would absolutely be looking for the resultant. You can call it capital R, and I'm going to be insistent you have to have an arrow on the resultant. Every year I have some kid who thinks that the resultant is just this. But the problem is now they don't know where the vector is originating from. They don't know where it's pointing to. They don't know where to put theta. They don't know which angle to find. So put the arrow on the end of it because that's which way it's pointing. I have not covered everything with you. For example, number 7, see if you can figure it out. For example, number 3, see if you can figure it out. I will put an answer key online, or else I'll go over the answers next class. Class is yours.